in some of the other devices I show you too. Move ahead to the next slide. Just a quick example of the technology. We've got a sender source, sends a laser beam through the measuring path to some receiver optics that takes the light through the fiber optic cable back to a receiver that's also mounted in the optical head. So, it's fairly straightforward, not a lot of moving parts. We're just quantifying the amount of light scattered off the dust and correlating that back to a dust concentration. Next slide. Wet gas, of course, is a little bit trickier because water droplets attenuate light just like dust particles. And so to get an accurate dust concentration measurement on a wet process, you have to eliminate the dust or water droplets. And so we've developed this device, FWE200, and again, we're using the same scattered light technology with the probe, but we're simply pulling a sample through a thermocyclone, heating it above dew point first, and then monitoring it above dew point to eliminate the water droplets. Next slide. HCl is, I would say, it's not as easy to measure as things like CO and CO2, O2 in terms of sample handling. There's a lot of things you need to consider when developing a CEM system for measuring of HCl. The two most important things are that you keep the sample hot and wet. HCl is very water soluble, and if you were to drop, especially at the levels we're talking about with the MACT rule, if you were to drop that gas below dew point, like in a wet or in a chiller, you would simply scrub all the HCl out, and you would be left with nothing. So for accurate measurement, you must keep it hot and wet. An example based around the 3 ppm limit of HCl in the MACT rule was that you must keep it at least 185 degrees C to avoid absorption effects and salt formations in the sample system. And a quick flow rate also helps to avoid loss in the line, and our standard would be about above 5 liters per minute. We've got quite a lot of experience measuring HCl using CEMs, and it is doable, but you have to take very close care of the sample handling. Similar to the discussion we had on mercury and how do you handle mercury, HCl offers some similar challenges. One of the biggest challenges for HCl is calibration. Transporting of HCl in a wet state coming out of a flue gas is generally quite easy as long as you follow the rules and you keep it hot and you move it fast. The problem comes when you try to inject a dry calibration gas into a sample line, and then you're dealing with a situation where the HCl reacts with the lining of the sample line, and we get absorption, desorption effects. And in general, if you were going to, let's say, for example, inject a cal gas of 3 ppm onto a system with a 100-foot sample line, I think you would probably expect to run the bottle completely out of gas before you would ever see a response on the analyzer, because that HCl that you're pumping in the system would be absorbed by the sample line itself. So, but if you can get it in a wet state, then the water and the HCl compete for the absorption effect of the sample system. Excuse me, and the water tends to win, and you get much better and quicker response of the HCl. So in our discussions with EPA, there's going to have to be some consideration for calibration of HCl, and how do we do that in a wet way to develop a wet cal gas or a humidified cal gas that will be able to transport all the way up to the probe and back to test the entire system. Next slide. I mentioned earlier that the performance spec listed in the original PC MACT rule was referencing an FTIR analyzer. The EPA, as I mentioned, is accepting other technologies. We also manufacture an FTIR device, but our best solution, and I think we would define a best solution based around replacement of an entire system, and then including HCl in the new system or adding HCl to an existing system, would be what I show you here. The first device we talk about is an infrared measurement using gas filter correlation. This is our MCS100E. A lot of you in the cement industry are probably familiar with the MCS100E. It's quite extensively used for CEMs. It's a multi-component system, so you can simply, if you had one, add an HCl channel to it, or you could add the measurement of HCl to a new system if you had decided as part of your evaluation process that the older system was near the end of its life and you were looking for something new. You could add HCl to a system that included SO2, NOx, CO, CO2, O2 in one monitor. The tunable diode laser spectroscopy method is a little bit different in that we use a laser light at a very specific wavelength, where instead of using a broad IR measurement with the MCS, we use something that's very focused on the specific component, in this case HCl. Gives us a little better sensitivity and a little better cross interference than we see with the MCS. But the disadvantage then is it's a single component, but if you had an existing system that was quite new and you wanted to integrate something into it, an analyzer like this is something that you might want to look at. Next slide. Just a little bit of detail on the MCS. I mentioned it's a multi-component device, undiluted hot-wet, which meets our criteria for HCl monitoring, and we use IR absorption with gas filter correlation to make the HCl measurement. We have I would say over 1,000. There's probably 1,500 units installed worldwide, most of those measuring HCl and other water-soluble components. So I mentioned we had a lot of experience with HCl, and this is the analyzer we have the experience with. Next slide. This just gives you an idea of some relevant measuring ranges. I highlighted the HCl for the purposes of the conversation here, 0 to 10 ppm, which is probably about right where you'd want to be, considering that the HCl level and the reporting requirements are a 30-day average. You're going to see some instances where HCl can be elevated in the process. So, lower detection limits of about 0.1 ppm at this range. So it's quite able to handle the requirements of the MACT rule. Next slide, please. The TDL, again, as I mentioned, is a single component analyzer using a selective laser to measure a gas component of interest, in this case HCl. The advantage, of course, is we get a lot higher sensitivity and minimal cross interference, and you'll notice then we also get a much lower range of about 0 to 5 ppm HCl full scale on this device. And with the proper integration, you could pull a sample off of an existing sample system and run this through. Depends on the setup and is the sample system from the probe to the heated line already controlling at a proper temperature to avoid salt formations and loss and that kind of stuff. But theoretically, you could integrate this into an existing cabinet and measure HCl as a single component. Next slide. Here you can just see a little bit of the internals of the device. Probably not too interesting for most people, just the fact that we've got the laser source and the detector and a constant reference channel, so we're always measuring a reference against the detector. And then we use what we call a multi-pass cell, so we're shining the light back and forth multiple times to create effectively long path lengths in a short footprint. And that's what helps us to get to the low levels, like we saw with the 0 to 5 ppm. Mercury SEMS. Carl talked a lot about Mercury SEMS, and obviously TechRan's got a lot of experience. SICK has been doing mercury monitoring themselves since about 1990, mostly in Europe and waste incineration and those kind of applications. And when the applications came to North America a few years ago with the camera rule, we decided to take a step back and say, is the technology where it needs to be to meet the requirements? And if we could start from scratch and design what we would consider a best measuring system for mercury, and this is kind of a general question we asked, what would it look like? And so we came up with these 4 criteria. The first, because mercury is sometimes difficult to transport, and Carl mentioned the issues with mercury chloride transporting, it would be best to be able to measure it right in the process. But because we have to convert everything over to elemental mercury first before we can measure, we can't do it in situ. So our solution then, we would prefer to keep the sample line as short as possible. The second criteria was, let's generate the conversion from mercury oxides to elemental mercury without the use of any consumables. There are some devices that use converter materials and temperature to convert. Our old device used the wet chemical conversion with a tin chloride bubbler that we did the conversion, and we wanted to avoid any sort of consumables, so we went with a high temperature conversion method that gives us 100% conversion without any consumables. Most importantly, on the measurement method, we wanted something that would be very limited in terms of cross sensitivities, or if there was cross sensitivities, we could very easily optically correct for those in real time. And we also wanted it to be continuous, and so we wanted to get rid of gold traps and things that maybe slowed down response. And as we discussed in the earlier presentation, the wide-ranging concentrations that are seen in the cement industry through varying raw materials and as well as conditions like raw mill on, raw mill off conditions necessitate an analyzer that will be able to give you a very short response time. And of course, it has to have automatic checks with span gas. Next slide. So we came up with what we're calling our Merchem 300Z. This is actually a quite new device. It's just off the assembly line, so to say, I guess. And it consists of a pretty basic system, sample probe, which is a standard sample probe, something we would use on our multi-component IR analyzer, for example, heated umbilical, and then the cabinet itself. Next slide.